Okay, now let's try to do similar thing, but using same restraint. Okay, so let's do for now everything as it was. So we have just these, they are fully occupied. Let's split the atoms without any extra restraints. Split. Oh, I have to click the atoms that I want to split. Split. I'll just rotate a bit. That didn't work. Okay. So like that. Should be more or less what we want, right? Okay, so we split the atoms. Again, let's do simu on all of them. Not on this. We don't want to restrain these. Okay, so we have highlighted these, simu 0.01, let's say, regu default. And now let's do sorting again. So we will sort them. Now for the changes to work, we should do refine, but we don't want to do refinement before introducing restraints. So what we can do 0 cycles of refinement. So it will just basically write a new inst file without any like refinement, right? Okay. And now let's have a look at our edit. Let's have a look at the inst file. So in this case, we have very nicely arranged column. So we have atoms that are in part 1 and atoms that are in part 2. So we want to do two things. So first, when we use same, we want to compare the first component of this order to the second component. And that's super easy. We just write, instead of C1 to C2, C3, C4, blah, 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 we write C1A, C2A, C3A, C4A, C5A, C6A, C7A. Great. Now, another line. And maybe just for practice, in this case, let's try to not approximate benzene ring as 6-fold symmetric. Let's say that the molecule has a mirror plane. I think we can all agree that this molecule has a mirror plane, right? So if it has a mirror plane like that, from top to bottom, that means that atoms C1, C2, they stay the same, right? But C3 will be converted to C7, C4 to C6, C5 will stay the same, right? So we have to reflect the differences in the distances using same command. So how are we doing that? So after all, we want to reflect this inner mirror symmetry in the restraint. So how do we do that? Atoms C1, C2, they stay in the same place. We just write C1, C2, right? And now we normally would put next atom, which is C3, right? But we know that C3 is equivalent to C7 because of symmetry. So we will write C7 to reflect this inner symmetry. C7. What about C4? Sorry, C4 is equivalent to C6. C6. And then we would write C5, and it says in the same place, right? C5. What next? We would like to write C6, but we know that C6 is equivalent to C4 because of the symmetry. So again, instead of C6, we write now C4. And I think one more atom is what is left, C7, but we know that it's equivalent to C3. So we write C3. Let's see if we have 7 atoms. 1, 2, 3, 4, 5, 6, 7. Okay, looks good. So we can write now save. Okay, so we wrote the geometry restraints, we wrote the ADP restraints. So let's do some refinement. Control R. Nice. Control R. Okay, we can make them anisotropic. Control R. Okay, looks good. Now, I mean, here it's not really necessary, but if you want, if we will just look at show part 01, another restraints we could introduce is to make the benzene ring flat, so we can write flat. Well, it's not necessary in this case. It refines as quite planar, right? But yeah, just for practice, we can do similar thing for that ring. And usually, if you need to use flat, then you probably need to use stronger, like larger strength, for example, 0.001. But yeah, let's just leave it as default in this case. Okay, and again, show part 0, 1, 2. Control R to refine. Yeah, it won't really change. And H add. Okay. So we could now update the formula. Something is wrong, and the thing that is wrong here is the Z number. It doesn't match P minus 1. So we can do edit and just change 0 to 2 instead of 4. It will automatically update. If we do refine, well, it didn't for some reasons. I think yeah, 2, save. Yeah, now it works. It's changed, so our atom count finally looks normal. We could optimize weights. Do some more refinement. Yeah, it's essentially done. Okay, so last thing I wanted to show you is to show you what OLEX actually does. So let's come back to the model where we had just the model without accounting for disorder. So we want these to be carbon atoms, naming. Let's do the automatic naming. We want to start with 1 carbon. 1, 2, 3, 4, 5, 6, 7. Escape. Okay, refine. So let's see what happens if we allow OLEX to write its own restraint. So yeah, same regu, whatever. Let's select atoms we want to split, same regu. Okay, let's shift it a little bit, somewhere there. Yeah, that will do, I think. Yeah, and also let's add simu. Oh, we added simu. No, we didn't add simu. We added regu automatically. So simu, Control R. So Anis, and let's have a look at the restraints that OLEX has put on the model. So I will just click on these atoms that are involved in disorder. Let's have a look. So OLEX wrote a lot of restraints, but what did it actually do? So firstly, when OLEX applies same, the way we did it, it actually doesn't do same. If it writes a lot of SADI restraints that should be kind of equivalent to the same command, but it just does it by writing a lot of SADI restraints instead of same. But what it also did is, let's have a look at this line, SADI, C2, C3, C3A, C2A, right? C2, C3A, C3, C2, the same as C3A, C2A. And another line, C6 to 7, the same as C6 to 7, the same as 6 to 8 to 7A. So what it did, it compares separately all of the distances. This pair, this pair, this pair, and blah, blah, blah. So I usually don't like it to do it this way. I prefer to, for example, if you have something that is yeah, like benzening 6-fold symmetric, I prefer to write down restraints by myself because I think that this way they are kind of more chemically correct, right? But yeah, so I usually only use Olex to when I split and I decide to use same, then I let it go whatever it does. But then at the end of the refinement, I actually delete all of the Olex restraints and I put my own restraints. Yeah, so just always be careful and try to understand what Olex actually does, because it will do many very useful things for you, but not necessarily what you want. Okay, so we basically finished, and let's just have a look. Let's do it as Olex. Let's have a look at the CheckSIF report. I tested it before, and the way we did it with the Olex's restraints, it doesn't really matter for the CheckSIF. So we can just finish this way and have a look what's happening in the CheckSIF file. Let's do more refinement cycles and also the things that I mentioned. Let's change 4 to 2. "20 cycles. Two years later. Okay, that's almost optimized, but let's also click ACTA. And if we do ACTA, it means that Olex will actually create the CIF file that we will be able to pass through CheckSIF. Okay, that looks optimized. We can also, just to be sure, look at the bond lengths a little bit. Yeah, 1.49, 1.5, yeah. What about benzene rings? 1.37, 1.37, 1.41, yeah. Okay, and we can do report. And again, these things, we didn't input anything, so we'll get some alerts during the CheckSIF, but yeah. Let's see what other alerts exist for those that are related to lack of the information in the CIF file is going to show us. We wait a little bit. Maybe in the meantime, I will just show you packing of these molecules in the solid state, because I think it's kind of interesting. I think is that structure. So I will open it in Mercury. Okay. So yeah. And if we explore short contacts, actually, that's not what I wanted here. We can see that the titanium cations, radical cations, actually form kind of columnar stacks with toluene molecules, right? And these kind of pi stacking interactions probably are related to the properties of the crystal. So even if you put crystals of that compounds at high vacuum, it doesn't actually lose solvent that easily. So yeah, and we can see that here the sulfur is kind of up, and here it's kind of pointing down. Yeah, so we got now the CheckSIF alert. Let's have a look what's happening. So all of these are related to missing information that we didn't input, so we don't look at that. Calculated reported moiety formula strings differ. So you can see that basically it's just a matter how formula is presented. Right here it's just reverse order, blah 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 blah. That's again. Here are some things, and in the case of this structure, it's probably related to the fact that it forms these stacks, and because of that, ellipsoids are kind of elongated in one of the directions, which kind of reflects the kind of movement in the stack. This is something that is related probably to the fact that the crystal is not entirely single, but again, they are all sea level alerts. It's not something terribly bad. That's something quite common when I measure stuff on our instrument, even with very good data. And yeah, we have something that's probably a reflection that could be omitted. Yeah, but we would have to investigate it properly a little bit more. I think it's just the way that it was refined this time, for example, because we use these OLEX-based restraints. When I did it without them, when I wrote them by myself, this checksif alert was not here. And here are some G-level alerts. Basically, yeah, it contains CMU records, it contains some SADE records. We have some other restraints. Some disorder in the structure, short intermolecular contacts, and they are just contacts between these kind of fluorine atoms. We have some labels that we didn't change. Basically nothing bad. So with this file, I would still play it a little bit more to make it look better for publication, but in general, yeah, everything looks fine in terms of the results of the refinement. So I hope this video was useful to you, and I will try to record some more videos in the future. So see you again.